Hello and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 814, binary tree pruning. Given the root of a binary tree, return the same tree where every subtree of the given tree not containing a 1 has been removed. A subtree of a node is a node plus every node that is a descendant of the node. Jeez, that is horrendous English. Anyway, let's look at some examples because Leetcode's problem statements are generally pretty bad. So if we look at this tree here, we can see that, we start at the root here, and can we remove this node? 1, no, because somewhere in its children, there is a node with a 1. So therefore we can't remove this node 1. Can we remove this node 0? No, because its right subtree is actually a 1, so therefore we can't. And then can we remove this node 0? Yes, because it actually doesn't have any children, which are 1s, right? So we can remove this one. So that one goes bye-bye. And we're left with this tree here. Let's look at this example here, where the root is a 1. So obviously we can't get rid of it. So we're going to look to its left and its right children. So we go to the left, and we're going to ask, can we delete this node here? And maybe let me zoom in a bit so it's a little bit easier. Okay, the image is terrible. Anyway, so we're at this 0 here, and we're going to ask, can we delete it? And basically what we have to do is make sure that there's no there's no 1s in both the left and the right subtree. So we're going to go and we're going to say, okay, does its left subtree contain any 1s? And it doesn't, because it's just this node 0. So we can delete this node because it doesn't have any children with 1s. And remember that we still need to check the right side. So this one doesn't have any children with 1s, so we can delete it. And since we deleted both children from here, we can actually delete this node here. So we've taken care of the left subtree of our root. Now let's go to the right. Can we delete this 1? No, we can't. Obviously it's a 1, we can't delete it. We're going to see if there's any deletions we can make in its left subtree. So we get to this 0 here, and obviously it's a leaf, and we can delete it. And then we check the right subtree of our node up here, and it's a 1, which means that we can't delete it. So we can only delete the 0, and that's what you see what we're left with, right? These 3 nodes here. And for example 3, we're going to do the same thing. Okay, we start at the root, it's a 1, so that means we can't delete it. We check the left subtree, it's a 1, we can't delete it. We're going to check its left subtree and its right subtree. The left subtree is a 1, so we're going to check its left and right. It doesn't have a right, so we only check the left. And we see that it's the 0 here, which is the leaf, so we can delete it. And then since obviously we didn't delete both children, we can't delete it. Plus this is a 1, so we don't have to worry about that. And then this one's a 1. It doesn't have any children, so nothing to delete there. So we've checked the left side of our root. Now time to check the right. So obviously this is a 0. So in order to delete this node, we have to be able to delete both the left and the right. So we're going to check the left. Can we delete it? Yes, we can, because it's a leaf and it's a 0, so we can delete it. Then we go to its right, and we see that we can't delete it because it's a 1, so that means that this node here stays, and that's all the deletions we can make. So this question is definitely one that's quite simple to look at an example, but actually coding it up is a little bit more complicated because we have to not only worry about the children's values, but we have to basically pass those children's values up to the parent and make sure that we can delete the parent. So this is going to be a post-order traversal because we want to check whether or not we can delete the children and then pass that information up to the parent and then make a decision of whether or not we actually need to delete that parent. And that's why it's a post-order, right? We're going to do the children first and then the parent and then pass that information higher up the tree as part of our recursion. That being said, at this point, I want to move to the code editor because it's going to be a whole lot easier to explain than trying to draw out with diagrams because these trees can get really messy. So let's just go to the code editor and I'll walk you through it line by line. It's really not as hard as it may seem at first. So I'll see you in the editor. We're back in the code editor. Remember when I said that this problem is going to be hinging entirely on all of the weird edge cases and intricacies? Well, let's go through all of them because there are quite a few here and it's easy to get mixed up and miss one, which is going to cause you to not actually get the solution. The first thing that we want to handle is actually the base case, which is we're given an empty tree. Obviously there's nothing to prune, so we just return none. So we're going to say if not root, then we simply want to return none here, right? Now what we want to do is we want to go through our DFS in a post-order manner. And what we're going to be doing is we're going to be checking whether or not we should be deleting a node. And the way that we're going to determine that is whether or not the left subtree or the right subtree of a current node actually contains any ones. For example, if we have this node 0 here and we ask ourselves, can we delete it? Well, we have to make sure of 3 things, right? That this node has to be a 0 first of all, and that both of its children have to not contain any ones. So obviously there's a 1 in its right subtree, which means that we cannot delete it because that would, break this link here, and we need all the ones to stay in the tree. So what we want to do is we want to return from our DFS function whether or not we should actually be deleting a node or not. And what that's going to mean is we're just looking for, does my subtree have a 1 in it or does it not? So that's really what our DFS function is going to be. And then based off that, we can do our post-order traversal, because we're going to be processing the children first, passing the information up to the parent, and then making our decision of whether or not we want to prune or not to prune. So let us actually think about what's going to happen here if we have the entire tree being 0, which is another case. If the entire tree is 0, then what we're going to be returning from our DFS function, remember that we just said the DFS function is actually going to return true or false, whether or not our trees actually have a 1 in them. If we call our DFS on the root and it returns false, then that means the entire tree has zeros, and that means that we need to prune the root and get rid of everything. So we're going to say return the root if self.dfs of root. So basically we'll be pruning it as we go, but if this returns true, then we can just return the root. If it returns false, that means that this is the case where the entire tree is actually null, and we just need, 0, and then we just need to return null here. So we're just going to return null or none if the self.dfs function on the root actually returns false. So that's the easy part. Let's actually define this DFS function. So it's going to take a node, and obviously with most post-order DFS questions, what you want to do is actually make sure that you have a node to work with. If you access the left or the right child of a leaf, obviously you won't have any nodes to work with, so you need to make sure that you're actually processing a valid node. So we're going to say if not node, we can simply return false. We can just treat it as if it was a 0, because if we prune a null node, it doesn't matter. We're just setting it equal to none. Nothing's really going to change. So we return false in that case. Another base case that we need to handle is actually what happens when we're at a leaf. Obviously, if we look at this one, the decision of whether to get rid of a leaf depends on whether that leaf actually equals to 0 or 1. If it's a 0, we want to get rid of it. If it's a 1, then we don't want to get rid of it. So we're going to say if not node.left and not node.right. So basically, if we have a leaf, we want to return whether or not node.val equals to 1. So that's going to determine whether or not we get rid of it. If it equals to a 1, we'll return true, which means that there is a 1 in that tree. And if we return false, then that means that there is no 1 in that tree and we can get rid of it. So we're going to have our 2 variables here representing our post-order traversal, where we go into the left and the right. So we're going to say, does the left have a 1 is going to equal to self.dfs of node.left, and we're going to say, does the right have a 1, and that's going to be equal to self.dfs of node.right. Now we need to go through all of the cases where we want to delete something. So let's go through the most simple one, which is actually that there's a 1 in both the left and the right, which means that we cannot delete the current node because obviously both of its children have 1s, therefore we cannot delete it. So we're going to say if the left has a 1 and the right has a 1, we can't do anything. We have to keep the node. So we're going to return true because, in the subtree that's going to be formed by basically taking that node and its 2 children, there will be at least 1 in there somewhere. So we just return true. Otherwise, we can now have the case where the left has a 1 and the right doesn't have a 1. So not R has 1. So basically, it would be the opposite of this case where, here we have that the left actually has a 1, but the right doesn't. The right does have a 1, but the left doesn't. This case would basically be the opposite of that. So if the left has a 1 and not the right has a 1, then we want to be pruning that right side because we don't need it. It basically has no 1s in it, so we can get rid of it. So we're going to say node.right is going to be equal to 0 because we can, we know from this not r has 1, that there's no 1s in the right subtree, so we can just set the entire thing equal to 0, and we're essentially pruning it. And now what we want to do is here we want to return true, because obviously the left subtree has a 1, so our current node cannot be deleted. So we just pass that information up to the parent in the post-order DFS. Now we're going to handle the opposite case to this. So we're going to say else if right has a 1 and not left has 1. So this is this case where the left tree doesn't have a 1, but the right tree does. So what we want to do here is we just want to say node.left this time is going to get pruned. So oops, we're not setting it equal to 0. Apologies. We want to set this equal to none. That's how we're going to prune it. Yeah, so we set it equal to none. And this time the left is getting set to none. And we just want to return true again. And then we have the last case here, which is that both of the, both of the children are actually zeros. And whether or not we delete our current node will depend on whether the current node is actually a 0. If the current node is a 1, then we simply prune its left and right children, but we keep the current node. If it's a 0, we just prune everything. So we're going to check if node.val equals to 1. What we want to do is we just want to get rid of its left and right children. So we're going to say node.right equals to none. And therefore we will have pruned the left and the right. In this case, we want to return true because obviously we have to keep the current node because it equals to 1. We can't prune it. Otherwise, we're just going to return false. And in the next iteration, we will end up pruning our node here. So let me just run this, make sure I haven't made any simple syntax mistakes. And it looks like I haven't. So let me submit this and it works. Excellent. So what is the time and space complexity of our algorithm here? Well, this is a post-order depth-first search. So with any post-order depth-first search, it's going to be big O of n, where n is the number of nodes in the tree. Pretty straightforward here. Space complexity-wise, it's also going to be big O of n. And the reason for this is, even though we didn't define any variables for our solution here, this is a recursive depth-first search solution. And with any recursion, you have implicit stack frames associated with that recursion. Therefore, you need to count those as part of your solution. And in the worst case, that's going to be big O of n. But we do want to preface that some interviewers may not actually count their stack frames. They don't care. So we're going to say it's going to be big O of n if counting stack frames. Otherwise, this is going to be a big O of 1 solution. So you can kind of just present this to your interviewer, and this shows that you're thinking about, the cost associated with running the recursion, and you really basically can't get the space complexity on this one wrong if you say this, because, both answers are technically true, and your interviewer will see that you're actually thinking about more than just, did you define a variable or not? So that is how you solve binary tree pruning. Like I said, pretty straightforward post-order solution, though there are, a lot of edge cases that you need to worry about. As you can see, this one took me quite a while to figure out the first time I did it, but once I was able to figure out all of those edge cases and how to sort them out, it wasn't really that bad. So hopefully this video helps you figure out how to solve this problem. Anyway, I'm going to stop blabbering. If you like this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, please subscribe. I have tons of videos and I plan to make a whole lot more, so you don't want to miss those uploads. Subscribe to the channel. Otherwise, thank you so much for watching and have a great rest of your day. Goodbye.